Hi everyone, today we're going to talk about differentiating implicit functions. To begin with, consider this function here. You'll be familiar with its form. It looks like this. So the way it's written is, we've got a function, it's got two variables, and we can interpret this as saying that y depends on x. So like x is the input, we put it into this function, and then y will be the value coming out. And here's the graph, so x goes along the horizontal and y goes up the vertical. Given a value of x, the function will give us a value of y. Such a function is called an explicit function. As the name suggests, y is expressed explicitly in terms of x. It's quite clear here what the output variable is and what the input variable is. Now let's rewrite this so that we take both variables to one side. So suppose I were to give you this equation. It's the same equation, but now the way it's written, where all the variables are on one side, it's not clear what the input and output variables are. The variables basically are just jumbled together. So it can be written in this form here. We've got two variables. Some function g, this is the left hand side, of two variables being x and y, equals some number. This c denotes some number here being 1. So that's what an implicit function is as well. The variables are on like one side, and you can write it like so where you've got a number on another side. In an implicit function, it's not clear what the input and output variables are. So why do we have to consider implicit functions? It's because in some like applied math problems like economics or physics, the equations might come in implicit flavor. Question: can we turn an implicit function into like an explicit function so that we can differentiate normally? Sometimes yes, but sometimes no, and that's why we have to learn techniques for implicit differentiation. So in this case, where I've got this equation, it's quite obvious I can rearrange y in terms of x and use normal differentiation. But we can also kind of do implicit differentiation on this form, and we'll get the same answer. Okay, let's consider some more examples of implicit functions. So here is an implicit function. You've got two variables, and you've got a number on one side. Here's another one. Now this one's can be taken like as an example from a utility function in economics where x and y represents goods. This third example, a is a constant, k and l are variables, and this is an example of like a production function from economics. These three examples are implicit functions of two variables. This final one, we've got three variables, q, k and l. So this is an implicit function in three variables, like so. I'm going to show you today examples of differentiating. In fact, I'm going to differentiate all three of these functions using implicit differentiation, and also for the third one as well, where we've got three variables. Okay, now let's go back to the first equation, it's quadratic, and let's just differentiate it two ways. First, written in terms of explicit form and implicit form. So let's do this one first. So dy by dx is equal, using the standard rules, x squared, 2 down, x and 1 off the power there, plus 5. Now let's write this thing as an explicit function, i.e. since we have two variables x and y here, that. Okay, so this is now the function in implicit form. So how do you go about doing differentiation when it's implicit? Is we first of all need to know what we want first. So we want dy by dx, not dx by dy. Now if you write it like this, this tells us kind of what the output is. It's y, because we want to see how y changes as x changes. So that's completely different to if we wanted dx by dy. So this is not the same as dx by dy. So first of all, we need to know what the question is. Okay, so that means as x changes, y changes, so like y is the output. Now when we look at this, I think you need to know this is like you've got the two variables, they got to combine in such a way that when you add these three terms together, it comes to 1. So if x is some value, any value, then y must adjust accordingly so that this equation is always satisfied. In other words, y depends on x. If x changes, y has got to change accordingly. So what we can do here to make clear what we've got that y depends on x, we can just put a bracket around it, so it's like a function of x, just like we usually write, fx to say that the function is a function of x. Y is a function of x. Okay, that here we don't really need to do it, but later on we need to do this to clarify in our mind what's going on. Now what you do is you differentiate each term with respect to x, so d by dx of both sides. So take d by dx of every single term, and if you do that, okay, so the step one, I've just done that, d by dx of both sides. Now dy by dx, this goes to this, minus differentiate 2x with respect to x, that's minus 2x, differentiate 5x with respect to x, it's minus 5. Differentiate, that's a constant with respect to x, so that's 0. That's step 1. Step 2 now, just rearrange for dy by dx, and that's our answer. So dy by dx is equal, take these both to the other side, 2x plus 5, that's the answer. And it's the same answer as if we did it directly using the explicit form. So here there's no difference, and you wouldn't really do the implicit differentiation here because it's easy to get the explicit one. Now consider this example. We need to do the chain rule here. Want dy by dx. Now what does a chain rule, right, why do we need a chain rule first? Because we've got an inner function involving x, and there's some other function, an outer function on that function, on the inner function. So it's like a function of a function. And what the chain rule says is this: if we want the dy by dx, we want to find a derivative of y with respect to the inner function, u is the inner function, and then times the derivative of the inner function with respect to x. In this case, we look at this thing, we can see that this can take the form y equals u to the power of 5. So u is this bit here. So what this chain rule says is differentiate y with respect to u first. Okay, bring the 5 down, u power 4 times, now differentiate the inner function du by dx, that's u by dx, so that's going to be 6x, and then substitute what the u is, or rather substitute for what u is. Okay, and so here's the answer. Now we're going to be needing this chain rule when we're going to be doing implicit differentiation. Okay, now next example. It's a function of two variables. It's of the form, got all the variables on one side, a number on the other side. We want to find dy by dx, so that tells us that y is my output and x is like my input to the function. So in other words, y is a function of x, or rather y is defined implicitly, or you could say that y is a function of x defined implicitly by this equation. That's a better way to say it. So step 1, d by dx of each term. And once you get the hang of it, you don't have to write d by dx on every single term, you can do it in your head. So for the first term, that's just going to be 2x plus, now the second term, this is where we realize that y changes as x changes, so we just stick a little x here to show it's a function. Y is a function of x, y is a function of x, to remind ourselves that we're interested in how y changes as x changes. Now here is a function of x times a function of x, so that's the product rule for differentiation. Okay, 2 is a common factor, so it just comes out, so we just, product rule just goes, of differentiation goes, write one of the variables and times derivative of the other one. So if we write y first, times derivative of x with respect to x is 1, plus then now write this one, and derivative of this with respect to x. And here we do dy by dx, because y, this is where this bit comes in, y is a function of x. We don't need to write bracket x here, because remember, this is just to remind ourselves that y is a function of x. Likewise with this term, we're going to need the chain rule here, because y is some function of x. So the inner function is y of x, and the outer function is squared of that. So chain rule, take the 2 down, that's 2y, 2 minus 1 to the power is 1, times the derivative of y with respect to x, right here, 0. Okay, that's the hardest bit. Step 2, now just kind of rewrite it in terms of dy by dx. So we can see these the first two terms, common factor of 2, can write it like this, and these got common factor of dy by dx. Okay, so we have this. By the way, at the moment I'm seeing I've got a curly y and a big Y. They're supposed to be the same y. Rearranging for dy by dx, we have this. 2's cancel. And we should say, since it's a derivative, so long as the bottom is not 0. So it's for x plus 3y not equal to 0. And that's the answer. The first step, looking back what we've done, the first step is the hardest, and this is what you're going to need practice at. It's very easy, for example, to see that the third term, you kind of forget about the chain rule. You just go bring the 2 down and y, but you forget about this term. Okay, example 2. Let's look at, from economics, a utility function of two goods, x and y. So the two goods, x and y, they have to be positive, and here's my x and here's my y, and c is some number. For this graph, I've set c to equal to 1. But if you set it to be higher numbers, they're going to take the same shape. We're going to see, regardless of this number here, which has to be positive anyway, regardless of this number, the gradient we want, say dy by dx, is just going to depend on the location of where you are at points x and y, the values of x and y. Okay, anyway, before we go, if you're alert, you can see that anyway. If we want to dy by dx, we can just rearrange y in terms of x and c, and use explicit differentiate, and that's explicit function, use normal differentiation. But let's just practice the implicit way. So step 1, I do d by dx, because I want dx here, of both sides, and we can see that this is going to involve product rule. So just like before, I just kind of remind myself that the output y is dependent on x, so I just do that by the y, and now I differentiate, do d by dx. So first of all, let's just write down the y and times the derivative of x squared, it's 2x. Just let me rewrite this so it looks more clear to you guys. So it's 2xy, okay, that's for the first term, plus, now I write this term involving x, just like that, x squared, times derivative with respect to x. It does depend on x because I put the bracket to remind myself, so I go dy by dx. Derivative of a constant with respect to x, that's nothing, 0. Second step, rearrange this expression for terms of dy by dx. We have minus 2y over x, and this derivative will exist so long as x is not 0, because you can't divide by 0 is undefined. So as I said earlier, wherever you are on this graph, the gradient dy by dx, for example, like that, this point here, for example, will just depend on what is the point there, what is the x value, what is the y value. That's all we need to know. And the sign makes sense, because if we look at here, any of the gradient, any line you draw like this, any slope, is negative. Now, just in case some of you are thinking about doing it the direct way, the answer from that will be, using the explicit form, okay, we get this expression. And if you look at it, you might say, oh, they're not the same, this involves a c and it's got no y in it. But look at what, and yeah, also the other thing is about, to get the dy by dx using here, we need the value c. If I have just a coordinate on the graph here, which is more natural, I'm saying I'm at this point here, I know that means I know what the x and y value is of this point, I can calculate straight away. But with this one, I need to know what my c is. Well, look over here, so that's rather inconvenient. But if you look over here at the utility function, c, whatever this number is given by x squared times y. So substituting c for x squared times y, I'll let you do it, you can see it's exactly the same thing. So we know for this example, implicit differentiation gives us a result that's pretty useful, because if I put myself, because the question is, I want the gradient at some point on this graph. If I pinpoint where I am on the graph, obviously I know the coordinate of x and y for that point. That's the x, that's the y. Whereas if I use this one, I need to know a point x. I don't need to know the point y. Instead, I need to know the value of this function c. Okay, now let's consider a production function from economics. You don't need to know economics to do this. A is just a constant, it is not a variable. Okay, in economics, K stands for capital, it's bigger than 0. L stands for labour, that's bigger than 0. C is just some number. So then we want, what is dl by dk? In other words, what is the slope of what they call the isoquant? Okay, so here is the curve. It's called isoquant. So it's connecting all the points, combinations of capital and labour. That gives us the same value of C, the level of production. I think I might have mistakenly said that this is isoquant. Well, it's not. That's the gradient of the isoquant. Okay, isoquant is just some kind of economic jargon anyway. So the way I've written it is like I want to see how L varies as K varies. So L will be some function of K. So it's up to you whether you want to by this L here, just put a bracket K there, but I won't do it because, you know, as you can see, as you get more practice, you can kind of just mentally know that that's what's happening. So it's just a product rule here. Okay, A is a constant, so it's not going to be affected, so it's just going to come out of the bracket, so let's just do that. Okay, so I've chosen first just to write this L to a quarter and then differentiate this thing with respect to K, so take the half down and blah. So okay, I've got that, plus, and now let's do it the other way around. Okay, now I've written this, and look at this. L, slow down here, bring down the quarter, L, quarter minus 1. Okay, if we don't have a calculator, remember quarter minus 1 is the same as quarter minus 4 over 4. That gives us minus 3 over 4. Now it's easy to close the brackets and finish, but remember L is a function of K, so we're using the chain rule here. So we've got to do a dl by dk, close brackets, and this whole thing now equals to 0 because that's a constant on the right hand side. And okay, so that's my dl by dk. So just to rearrange the whole thing, first I'm going to divide both sides. A is a positive number, so I can divide both sides by a. Okay, that gets rid of that. And then I'll take this whole lump over to the other side. Okay, which I've done. Now I'm going to take these over to the other side, so I times both sides by 4. In other words, take that up. L to the power of minus something is just the same as 1 over that something. So if I take it upstairs, that's just the same as saying get rid of that negative. So it's L to the 3/4. And for K, I have to take it downstairs. So that's K, same as K minus a half. Okay, you got to be careful when you're dealing these powers with fractions or stuff where you've got lots of messy copying out to do, because one slip and the whole thing is down the chute. Okay, so cancellation time. Right, so anyway, we've done the most important bit. The rest doesn't, you know, just method here. 2 goes into 4 2 times. Uninteresting, just write down the answer. Minus 2 L K minus 1, i.e. L over K, for K not equal to 0. Now, if you think about it more carefully, compare the production function example to the utility function. They're both kind of similar answers because they're both of the form something, let's call it x to the power of something, let's call it a times the other variable times to the power of something else, and might be times by something in front of it. Alright, so it's all it all looks like this. So it's not surprising my answers are exactly looking like that. So you can think about it, the treatment for this kind of production function, utility function is yeah, it's pretty much just the same, just differently. Okay, so the method that we use of implicit differentiation, where we've got a function of 2 variables, can be generalized to any number of variables. Let's push the boat out a bit and do one with 3 variables. So we've got 3 variables here. It's of the implicit function is of the form, we've got 3 variables. One variable is q, the other one is k, the other one is l, equals some number c. Say you want to find the derivative of q with respect to k. So I want dq by dk, question mark. Okay, so this is like saying, how does q change as k changes? Now I put the curly d here, so it's a bigger note as opposed to the straight d. This means this is the partial derivative of q with respect to k. This is saying, how does q change? How does the slope of this thing changes? As k changes, holding the other inputs constant. The other one is l. The other variable, sorry, is constant, so it's L is fixed. So let's try to express that again. You've got 3 variables, Q, K, L. This is saying, like, how does Q change as K changes, holding all other inputs fixed? Well, all other inputs is just L here. So we don't do a straight D. Okay, so to find the partial derivative q with respect to k, we just do the same thing. So let's go ahead. Now since L is fixed, q is just a function of L. So this time I'm going to do red ink here because this. So this guy is a function of k, sorry, k, not L, because L is fixed. Okay, L is fixed, so it's not a function of anything, and k is k. K is the thing that's just changing. Alright, so now we're ready. So first term, we're going to need the product rule. We've got a function of k here times k, and we're going to need the chain rule on this first term. So this is step one. Alright, so let's explain. This is what I've just done the first term. So product rule. First I'm going to just write the q cubed and differentiate this term with respect to k. Well, it's just 1. So that's that one taken care of. Plus, product rule says then next write the other thing down, is k, and differentiate this guy. Okay, now this guy, we know q is a function of k, so it's like a function of a function. Some function that's cubed. So use the chain rule, bring the 3 down, and take a power off. That's 3q squared, times the derivative of the q with respect to k, noting it's a partial derivative because we're holding something constant, the other variable constant. Plus, noting that we're holding L constant, it's just like a number, like 2 or 3. That means we just write that down, just basically just well, don't ignore it, but just it's there, and do this one. So that comes down 3k squared, and just write that. If it helps, just think of the thing that's fixed as a number, like 2 or 3 or something. Okay, plus the final term here. Now this one, again, it's like a product and a chain rule. So just at this stage, I would definitely encourage you to have a go and then just check your answer with mine. Okay guys, wow, that's a long expression. Right, that's step one. When you got such a long thing, go really carefully. It's easy to screw up. One lapse of concentration, it's gone. But we're only humans, so if it was an exam, you'd get method marks. So you understand the process. I'm sure that even professors make mistakes, typos in their classes. So now step 2, rearrange. I want dq by dk. So I collect these two, I look at that and I look at that, and I just gather them together like so, and then the other stuff I can just gather together and take it to the other side, so I can divide through by this thing here. Okay, the details aren't real important here, it's just simple adding, subtraction. Of course you do have to do it carefully, but anyway. Okay, so the whole answer is minus this ugly expression over that ugly expression. Alright, and this is what I have, that's the answer. Note in the bottom that you've got common factor k, so let's just scrub that out. K. Okay, so concluding remarks, implicit functions. Okay, we need to know how to differentiate implicit functions, because sometimes, given an implicit function, we can't isolate the what we call the dependent variable from the independent ones. In an implicit function, it's not clear what the output variable is until a question asks you, find dy by dx, or here dq by dk. We'll have to live with implicit functions because in some applied areas of math, functions come in implicit flavor. The method I've done here is for 3 variables. That's probably hard enough, but just know that this method can stretch to any number of, finite number of variables. And as always, just important thing is to remember the method, understand the method, and highly advise you to kind of think about, like, graphically, what does this mean, like I've shown you for the isocon and the kind of indifference curves. So finally, good luck guys, and lots of practice.